secondi,
Dimmi tu quando.
Vai.
Hello everybody, and welcome to the first webinar on 3dqsar.com. I am Rino Ragno, and I am one of the ideator of this site. And I will go straight forward to the first part of the seminar. So the webinar is divided in two main parts, and the very first part is on theory on QSAR and 3D QSAR, and then with some future application we will have. Then the second part will be in practical part. I will show you how to make 3D QSAR model either from pre-aligned molecules or from scratch, taking molecule from JMedChem, the very first journal on medicinal chemistry. So I will show you everything. So as you are almost all of you should be aware that the research on medicinal chemistry is divided into big branches: ligand-based and structure-based. Ligand-based are based actually on just the knowledge of the ligands, while structure-based need the knowledge of the target of the ligands. The main application softwares and theory on ligand-based are based on QSAR, pharmacophore approaches, and 3D QSAR. While on structure-based we have the scoring functions that are actually the base of any molecular docking models, and comparative binding energy analysis. There are somehow some bridge between ligand-based and structure-based. If you align the molecules using molecular docking, you can make 3D QSAR, so you have ligand-based / structure-based model. So, just a little bit of history. QSAR rely on the approach developed by Ansh and Fujita, that they had a good idea, the good proposition to put together several studies that they were done before, half century before of them, actually. And Ansh and Fujita, they had a very good idea in putting together their estimation of hydrophobic, electrostatic, and steric estimation of a list of molecules with the activity of the molecules, the Ki. And this was 1969 and 1964 actually, the very first papers. And but at the same time, Free and Wilson were also developing a new approach called actually the real QSAR. You have to understand that the QSAR that nowadays anyone is using, not the 3D QSAR, is actually the QSAR of Free and Wilson. The Ansh QSAR was based on descriptor on molecules, and actually with this descriptor they were estimating the delta G of any of the transformation of the ligand into the complex, actually without the complex because it's a ligand based, and this descriptor were used as an estimator of the delta G, and therefore is not a real QSAR but is a linear free energy relationship, while the one that were developed from Free and Wilson, they were related with the presence or the absence or some substituents on a list of molecules. And therefore this was the very first QSAR equation. And actually they actually invented the very first fingerprints, because they invented the indicator variables in, putting one when a contributor of a substituent was present and 0 when the substituent was absent. So a list of 0 and 1s in a binary constitution, and actually it was and it is the most used QSAR actually in the companies. So what is the procedure to build a QSAR or a linear free energy relationship model? First of all, you have to search for active ligands from a paper or from some molecules you have essayed from microbiology or something else, and therefore with the activity you have the description of the activity of the ligands. Then you need to describe the molecules, because remember you are talking about QSAR, quantity structure activity relationship. So you need to explain the activity, that is the activity of the ligands, and the structure. But the structure has to be described by means of descriptors. Descriptors can be molecular weights, number of rotatable bonds, volume of the molecules, or fingerprints that are actually nowadays much more modern than those used from Free and Wilson. Once you have these two little words described, you have to combine these two words with a mathematical bridge, and so to establish mathematical relationship among the descriptor or fingerprints and the activities by means of multilinear relationship, principal component relationships, and partial least square, and so on so far. If you want to make also classification models, this will be the set of another talk. Then once you have the model, you have to define the most important parameters and validate the models. So you have to calculate the coefficients, R squared, Q squared, the standard deviation error of prediction in cross validation, and so on. Then once you have the model, what are you going to do with the model? You are going to predict the activities of molecules you not have synthesized yet. Any QSAR, any model need to be applied. So any QSAR will be used to predict the activity of new molecules or untested molecules. The hurdles of this QSAR is that we have an equation. So the readiness of the models is very hard. So there is no relationship within the number and the structure somehow, apart from the fingerprints. So what are the limitations actually of the linear free energy relationship of the QSAR? So only deals with 1D or 2D structures. No 3D structure are embedded in any QSAR models, classical at least. So there is very difficulties in correlating these descriptors with the structure. No consideration of stereochemistry in the model. So this is a real a limit, because we know any molecules is going to interact with any given receptor or target in its three dimensionals, in a conformation, in a biactive conformation. So next one, we have to consider that there is some risk of chance correlations that have been very well reported in literature. QSAR is very good for classification. Anyway, its classification is another branch of QSAR. To read a QSAR model, you need to have a very well knowledge of the substituents, constants you are going to use. Sometimes these constants are very hard to understand, and most of them, the very best limits is that the series has to be an homologous series. Otherwise, you don't know if your molecules are going to act in the same way with the same binding modes. So these are it's not just a complete limitation of QSAR, but it can give you an idea. So let's jump on and to see how many QSAR we could have. We could have QSAR based on zero-dimensional descriptors that are actually related to numbers that are not giving you any information on the molecules, and are just related to the raw molecular formulas. So molecular weight, number of atoms, number of heavy atoms, number of fluorine, and so on. So then we can jump to the 1D QSAR, and this is related to the Free and Wilson QSAR, representation of molecule with fingerprints. So somehow here we have the importance of some parts of the molecules. but not yet any direct information how to modify the molecules. Then we have 2D QSAR, where the representation of the molecule is based on molecular graph or on constant. There are topological or 2D information. Then we have geometrical or 2D representation of the molecules, so using some conformation. Then we have the 4D QSAR descriptors that are actually the 3D QSAR plus a number of conformation of the same ligands. Then we can have the 5D QSAR, the 6D QSAR, just including induced field model, fit model. That means that in this part we need the conformation of the target, so we need to know how the molecules are going to interact with the targets. And at the end we can have the 6D QSAR that is considering 3D QSAR, 4D QSAR plus the solvation function of the complex that is going to be formed. So let's start to the 3D QSAR that actually are 4D, 5D, 6D, whatever you want. And these were introduced at the end of 80s. And the very first were molecular interaction field-based 3D QSAR. Then some similarity indexes methods as CoMFA was introduced. Then the pharmacophore was also used as 3D QSAR. Imagine how a pharmacophore is satisfied by the points and putting these points into a relationship with the activities. Then we have the structure-based 3D QSAR that is combined, where the interaction, the ligand receptor interaction are the energy are deconvoluted in per residues or per atoms. And then we have the receptor ligand scoring function, the ones that are actually used in the molecular modeling and molecular docking software. So molecular interaction fields are the ones we are interested more. In 1979, Richard Kramer, the inventor of CoMFA that we are going to see in a moment, with Milne, made the first 3D comparison of molecules, align them, and then making some comparison in the mapping of their molecular fields into a 3D grid. And this method was called DLOMS or DILOMS, I don't know actually what is the real pronunciation. Afterward, another approach was introduced by Peter Goodford in a few years later, that he was using the grid approach, that is actually molecular interaction fields calculated on proteins to try to understand how to fill up the ions in the 3D structure resolved complex. As you can see, if you want to go deeper into molecular interaction fields, there is a very nice book from Gabriele Cruciani from University of Perugia that he has collected a series of articles explaining the usefulness of MIFs. Here there is a representation how a MIF is calculated. You imagine you have a molecules, can be a small molecule or a target or proteins in a virtual grid, and at each node of the grid is put a probe atom or a group of atoms, and at each node is calculated the sum of the interactions between this node and all the atoms of the target that could be a small molecules. And these are, then you have the summation of this point, and these are the molecular interaction fields. And this is a way to describe molecule in 3D as the same way as receptors could see the ligands. Somehow the ligands are seen as a summation of electrostatic and static interactions. So, but at this point, either Kramer or Peter Goodford were just describing molecules. The rule of thumb was introduced with the PLS, the partial least square application, that actually the real name is projection of latent structures. So thanks to the Svante Vold and Hermann Vold, so the Vold family, this application was able to reduce the information into few new highly informative entities called principal components. And but at this point, the two applications, molecular interaction fields and PLS, were not connected yet. In 1988, Kramer and his group had a very nice and very good intuitions. They were the first to put together the two technology, MIF plus PLS, and they were the born of the very first 3D QSAR application called CoMFA, Comparative Molecular Field Analysis. And they developed this method inside a software, a suite of softwares called Tribos. And then if you, that actually it was actually a very lucky period for Tribos to have CoMFA inside. If you are interested in knowing how actually CoMFA was born and some details, please refer to this book written by Richard Kramer. It actually is the life of Richard Kramer. It's a half book in baseball and half book in molecular modeling. So it does work to continue to make a 3D QSAR. Well, actually, I just made a survey on 3D QSAR and CoMFA keywords on Scopus, and as you can see, while CoMFA has reached a plateau, the 3D QSAR is even growing exponentially. And why these two directions? Because CoMFA actually around this period was stopped to be commercially available, while some other 3D QSAR methods were inserted in other software house, and therefore this 3D QSAR is even growing. So we need to make 3D QSAR. So what is the CoMFA procedure? It starts from a training set. You have actually, let's start again this. You have molecular alignments. Then you are going to start the molecular interaction field calculation, model generation. And once you have the model generated, you have a bunch of coefficients that you can read graphically. So the real, very nice introduction from classical QSAR from Ansch and Free Wilson to 3D QSAR and ND QSARs was that actually you can read QSARs by watching at the coefficients and derivative of them and around the molecules that are aligned, and to see, for instance, here we have what Kramer called the semaphore rule, in the sense that if you have green, you can go to occupy this space, so you can grow the molecule. While if you have the yellow means break, so you need to reduce the speed and so far the static in this way. While on the other part you can have some electrostatic information. If you have blue, you have to increase the molecules to be able to donate lone pairs, so electrons. So you have to increase the molecule, the ability to make a hydrogen bond donator. And if you have the red, you have to increase the hydrogen bond acceptor around the molecules. So really, we are now able to how to modify the molecules very carefully. Well, okay, you may end up that QSAR is a magic point, is a magic software that can tell you everything. There are some critical points, and the most difficult points is to define the molecular alignments rules. So how to define the conformation of the training set molecules and how to overlap them. And these are actually very well described and embedded into the 3dqsar.com site. Returning to the original CoMFA article, Kramer was so good in underlying what were the strength of the CoMFA approach, and then he was actually using very rigid molecules and molecules very close conformationally, and he used 21 steroid-like molecules directly overlapped atom by atom, and actually so rigid that you don't need to make any conformational analysis on the molecules. So at this point, always in 1993, Richard Kramer also made some studies to define that 3D QSAR, unless QSAR, is a method that is not suffering of chance correlation. And this is very nice information. And what was the trick? That actually for 20 years, CoMFA prevented any 3D QSAR developing because they made a patent application. So for 20 years, no one in the world was allowed to make the application of MIF and PLS technology together. But at 2011, the patent dropped, and appeared the very first open 3D QSAR application by Paolo Tosco and Thomas Ballet, and they made the Open 3D QSAR, new open source software that now is not anymore developed, as Paolo Tosco is an employee of Cresset, and Cresset is actually selling a derivative of Open 3D QSAR. Very nice application, I would say, but is a sold software. And meanwhile, at the lab Rome Center for Molecular Design, we developed the 3D QSAR with open source. So we use R and AutoGrid to develop the MIF and to make the statistic. And almost in the same years of Open 3D QSAR, we made a very first tentative to make the 3D QSAR in an easy and open way. Well, in 2016, the time has come ready. That's the title of this slide. And actually, we realized that Java, Python, JavaScript actually, and several other libraries and pieces of software were available, and actually quite, not very easily, but quite easily to be combined to make a real 3D QSAR web server. That actually we started the real web server in 2007, but just in viewing, In 2016, we opened in August actually the very first 3D QSAR site to make very today in a simple way 3D QSAR model, and we called 3dqsar.com, as you are all about. This is the new phase of the server. This actually, we are now after 4.5 years at the version 2 of the site. In the site you can have at least 8 new applications. Not all of them open to the public, but they will be open, all of them, in the near future, very soon. There are several new, so like docking, PyCombine, and so on. And what is the site for? The site is to draw molecules from scratch. So there is a molecular editor, you can edit your molecules, or you can insert the SMILE structure and you draw your molecules from scratch. Or you can import molecule, as we can see in the second part of the webinar. And you can insert the activities and so on. Then the site is also for to make conformation analysis. You can ask conformation analysis with 3 methods. One is balloon, one is a code with RDKit, using the RDKit libraries, and one with the OpenBubble libraries. Then we have the availability to take this conformation analysis and make alignments with 2 methods. The shape method, developed by I don't remember the name. Okay, I will tell you later. And then the other way with RDKit. And then we have the way to make the PDB minimization and to prepare for molecular docking. This is under testing. Then we have molecular docking applications with two methods, MINA and plants, with all their scoring functions. Mikko Vaegno is the name of the guy, and for Babel and Shaep. Then we have the possibility to make 3D QSAR model, finally you would say, and with the possibility to choose several probes and several other settings that we are going to that I'm going to show you in the later. So then we have the combined models. This is a quite new way that is a full 3D structure-based models. There is a variation of 3D QSAR where the grid is not anymore a virtual one, but is actually the receptor around the molecules. And then the site is also very much used for teaching. As you can see in this paper I have published last year with 4 students and together with Richard Kramer, the inventor of CoMFA. Valeria, Martina, Stefano and Marco are 4 students from the University of Rome, and so pharmaceutical biotechnology course, and they were very happy to collaborate with me. And then the server is for research, of course, as maybe all of you is looking for. And as you can see, I have published in 2019 a paper describing that the PyCoMFA modules is good as the original CoMFA, and also is compared with the combination of Golpe and Grid applications from that were developed from Perugia by Gabriele Cruciani. And also you can see that the server has been already cited by 3 papers, one in the Journal of Molecular Structure, one in the European Journal of Medicinal Chemistry, and one in Journal of Computational Biophysics and Chemistry. All of them in a few months ago. And as you can see, you can use the server on any device, on a cell phone, and on a tablet, on a PC of course, as the server was designed to be responsive and it behave like an Android or Apple app. And this is also used anywhere, everywhere, I would say. At the moment we have almost 2,200 users, and many of them from India, from Italy because I use for teaching, and many of them from USA. And as you can see, the server covers more not 90 countries all over the world. This is a slide that is going to give you the roadmap of the site. Actually, as you can see, there is the PyMol edit where you can make the molecules, and then you can make the PyConf search, the conformation analysis that could be aligned, and to make the 3D QSAR model. This is the very first suites of app we developed. Then we inserted the way to make docking and to make combine. As you can see, you can make the same training set to make docking, molecular docking in a receptor, to make PyCombine. Also, you can align molecules into a key crystallize with a receptor, and to align them to a key, and then we have to have a combine by an alignment, make it by a ligand-based approach, and so on so far. You can make immunization to make PyCombine. So, and very soon we will have QSAR with multiple linear regression shape with PLS and also classifications, and we will have also explainability, and an easier way to read the QSAR and 3D QSAR, and all of this information can be downloaded and seen in a very good graphical environment such as USCSF Chimera. And do not forget, if you want to place questions and to be answered, there is also a module called PyForum to make questions to be answered. We are looking to checking the forum on a daily basis. So, what is the present, the future of the site? So, this is a free website to make 3D QSAR model from scratch. After 4.5 years, it is very stable. Of course, we are constantly looking for funding to go it up. We have made GPU integration to speed up MIF calculation. It is useful for either research or teaching. There is full structure-based 3D QSAR modeling. There is also molecular docking, under testing the way there is also some minimization of complexes retrieved directly from the protein data bank. Then we will have QSAR and model explainability. In the future, we'll have pharmacokinetic models, pocket recognition, scoring function, and hopefully a repository for models to be searched. And now I stop here and I give the scene to Alessio and Dylan Savoia that are going to introduce you the future implication that we will have on the site. We will catch later.
Hello everyone. I'm Alessio Ragno, and I'm one of the developers of the 3dqsar.com web portal. And first of all, thank you for being here. I will give you a little introduction on some new features that are coming to the portal. And together with Dylan Savoia, we are two students. We are actually currently graduating at the master's degree in artificial intelligence and robotics in Sapienza University of Rome. And so we are studying the application of explainable AI and graph convolutional neural networks to the field of pharmaceutical chemistry and drug design.
Alessio, ricomincia, non c'era audio.
Okay, so they told me there was no audio.
Vai.
No, questo devi fare. Solo mic. Okay. So we have had some problems. Okay. So AI brought huge improvements with the application of machine learning models, but the complexity of new neural network architectures made it difficult to explain which part of the input really is responsible for the output of the neural networks. And explainable AI aims to generate new models through which we can easily attribute the output to the input. As you know, there are several ways to describe molecules and to represent them in order to build some models. We can use descriptors, fingerprints, and smiles, but today we are going to focus on graphs. So why graphs? Through graphs we can exploit both the structure of the molecules and their chemical properties. So we will use graph convolutional neural networks to build some models and then explain which part of the models are responsible for their activity or some properties increasement or so on. So what is a graph? A graph is a collection of nodes connected by edges, and this makes obvious that graphs are well suited for representing molecules. So graph convolutional networks are specific neural networks which work on graphs using the concept of sharing information and spreading information among connected nodes. So we will have the information of one atom which will be spread to the connected atoms. The final output vector will then take into account the structure of the molecules and the features contained by each node. This is the classical graph convolutional neural network layer. So we use the adjacency matrix and the degree matrix, but this is a little bit too deeper than I wanted to go, just to give you an introduction of the layer. So we tested the GCN against using some models, trying to predict some properties, and we needed a benchmark data set to test if our technique was very good. So what we have here, if we used a data set of solubility, because solubility is a property through which we can actually easily see whether a molecule is more has a higher solubility than another, since it is a property which is which depends on the structure and on the polarity of the molecule. So generally, a molecule with more oxygens, I'll take me a little bit easy on it, but a molecule with a little bit more oxygens can be expected to have a higher solubility. So here we have two molecules. The second one has one oxygen, and our explainable model is able to attribute that the increasement of the solubility is due to the oxygen. You can see here we have an hydroxyl group, which is highlighted by the both methods of explainable AI, which are integrated gradients and input type gradient. So this is just to show you how we can use explainable AI and graph neural networks in order to predict new properties and generate new molecules and attribute the properties to the different parts of the molecules, and how we are going to implement it in the 3dqsar.com web portal. So this was just a brief introduction. After me, Professor Ragno will show you a practical example on how to build 3dqsar models and so on the portal. This was just to show you what's coming on the website. We are always improving the website, and we look forward for your opinions. Please contact us through the forum, and thank you for listening.
Aspetta, no. Okay.
Aspetta. Hi.
Oh, it's me again. Okay, now we are going to see the second part of this webinar that I'm very proud to do. And actually, I'm very excited, I would say. And here we are going to see some practical part on how to build 3dqsar models in a direct way. So first of all, again this slide, because I want to say you that with this site you may have the possibility to have an already aligned molecules, and with this all interconnection you may improve your models, because you can have an already aligned molecules, and maybe that alignment could be not the optimal one. So, and applying this to the original CoMFA data set, using as a benchmark, as Eugene Coates did, I developed a list of molecules, making some conformation analysis with balloon, RD kit, and open bubble, and to make alignment in a systematic way using shape with 2 scoring function and RD kit with 4 scoring settings, and using 32 different templates conformations from the data sets, and ended up to 192 by 3 alignments. And then the best one was also improved using variable pretreatment optimization to end up with an improved model, although the molecules were so rigid and easily overlapped with atom by atom. I got an improvement. So on the left you have the original alignment for the steroids, and on the right you have the new alignments. As you can see, there are several differences, especially on the most flexible part here. And on the left you have a table, on the left bottom side, you have the table of the application of CoMFA to the original data sets. And you see the numbers are quite comparable with the numbers that were published by Eugene Coates. And so at 2 principal components, the Q-square was 0.66, and then actually we got 0.68. And while for 3 principal components, it was actually overlapped. But the best one was we got the maximum Q-square at 4, but actually considered the small increment between the third and the fourth principal components. The best one is at 3 principal components. And after 192 by 3 alignments and VPO, we got an improvement of Q-square till to 0.935, an increase of about 30%, more or less, 25 maybe, and using just different alignments. In the same paper by Coates, they developed new models by variable selection with the fractional factorial design using grid and Golpe, and they reached almost the same numbers, but not this high. So just to give you a taste of what we can do with 3dQSAR.com. So now we are going to jump on the how to make ligand-based pre-aligned molecules 3dQSARs, to make 3dQSAR with structure-based aligned molecules, for instance, a data set of co-crystal structures, and to make 3dQSAR with molecules taken from freshly released articles in JMedChem. So if you go on this paper that I published in 2019, I have released 30 data sets already aligned, taken from the other articles. And then, with these papers, I just show that the CoMFA module was actually good in making 3dQSAR, but actually just one of them was very poor as the original one, actually, in making a model. We got a Q-square of only 0.19 without any doing anything on the dataset. And I will show you that I will go to use this dataset and to apply the VPO and the alignments to get a real good increasement. Then we are going to make I'm going to show you how to make 3dQSAR on already aligned by structure-based molecules from a paper we published in 2018 on DOT1L inhibitors, disruptor of telomeric enzyme 1-like molecules inhibitor. And this model was firstly developed with the 3dQSAR autogrid R using a force field from autogrid. Now we are going to see with the force field of CoMFA how it's going to behave. And then I have selected from the ASAP part of Journal of Medicinal Chemistry 2 papers. One was released on March 4th on molecules able to bind to the bromo extraterminal domain BD2 inhibitors, and the other papers from inhibitor of a kinase, AXL kinase. Okay, and then let's go to switch to the site. But first, I want to show you in these days that there were 175 applications for the seminar, and covering actually, let's see, covering, okay, we have students, professor, PhD students, postdoc, and even 10 from companies. And we covered maybe 39 different sites in the world. And here you have the points. You can see we are still covering much of the world with these applications. Okay, let's switch. This is the site. First, so I have two sites now. One that is open to anyone, and the other that is on my PC that no one can bothering with. So I have all the CPU available. So just to go to the applications, here we have the PyMol edit, and here, and this is an empty site. So here we can make molecules. The very first action we have to do is to add data set. So for instance, we can make a test just to show you very fast way how to make molecules, but this will be another tutorial to how to do everything. So we can select several stuff. You can write some notes and to give some information of the target, and if the molecules are already aligned, so if we have conformation already, or we are going to make some molecules. Just to see, we are going to make an empty data set, and then we can draw new molecules with a very nice molecular editor from MolSoft. It's an open source. Then we can actually, this is not working here, but you can, it's not updated. Okay, let's see. We can also take a molecule from the web, aspirin, and then we can modify. No, I didn't select it. And then we can also modify the molecules somehow. You can pyridine and so on. And then we can submit. You have to make a model, aspirin, and then we can make a molecules, a name, and we can give an activity. Imagine 6 micromolar into the training set, and the data set is test. Submit, and then we have 1 molecules in our data sets. If we click here, we have the molecule convert into 3D. Easily. Okay. Let's start with the practical part indeed. So I have here, open window. So, taking into consideration the paper we did, here you can have 2 tables, okay? The one that's describing what are the data sets, and the one that is comparing the published CoMFA or 3D QSARs with the PyCoMFA performance. And as you can see, here is the worst one. So from here you can go to these papers and to have the supplementary informations here, supplementary material. You can download the zip compressed file containing all the original dataset, and you can use that for exercitation. Right now I have already done, and I'm going to put this in. No, it's not here. Okay. Okay, here, applications. I'm edit. I'm going to delete this. I don't need anymore. Add dataset. We are going to start with the 82 dataset. These are the data are available as PIC50. That means the minus logarithm of the activity expressed as molar concentration. Then we have 82 from 3dqsar.com paper. and then we are going to put this as a generic enzymes. The molecules are pre-aligned. If you don't click here, the site won't allow you to make any 3D QSAR if the molecules are pre-aligned. Submit. We are going to create an empty data set, and then we are going to load molecules. I have the molecules in my PC here. Then I'm going to choose the files. Right now you should have all the molecules separated. That you cannot feed the site with multi-molecules files. We will put this option later on. Then we are going to, so I have this is the directory. I'm going to take the train set. In the original paper, the 28 molecules were divided in 18 as the training set and 10 as test set. Then I open the molecules, then I choose the files that contain the activities. And as I know the activities in PF50, the activity standard unit is P. That means minus log of. Then I go to submit. And then the site, I didn't load anything yet, but I can check if everything is okay. And then if I recognize it is okay, I can click here on load molecules. And now I have a data set. I can view my molecules all together, aligned. And then I can go back to load also the test set. And setting them as test set, of course. Test set, choose file. You see the molecules are in Mol2 format here, but any format that is recognized by OpenBubble can be used. Then I choose the activities for the test set, and I submit. I check everything is okay. I know it is okay. I've done this several times. Then now I have a list of 28 molecules. As you can see, you have pages of 20 molecules each, and then you can also show all of them. Clicking here. I don't recommend you to do this if you have more than 40 molecules. It's going to show to slower the visualization, not the site, but the visualization, because this is your computer. And then you have all the molecules. If you click on the molecule, you have the 3D structure, of course. Okay, now we are ready to make the models. We can go, since these molecules are already aligned, we don't need to make any conformation analysis or any alignments. We can jump here directly to CoMFA. Okay. And we can also view the molecules if they are all aligned. Somehow they could not be aligned very well. So these are all the 28 molecules. If you click here, you can just look at one. If you can click two, you can hold down the shift key and to have more of them, or just one. Or you can deselect everything and to show all of them again. Then we are going to go back to my molecules, and then you can push here build 3D QSAR, or to see the models that are already been built. We don't have any model, of course, here, and then we can build a model. I'm not going to describe all the options here. This will be another seminar, but we can select the Pro button I was describing earlier in the theoretical part, and then I suggest you not to move anything else, not to change anything else, and then to click just on submit to make the full model as the same setting in the original CoMFA paper. The only difference is that here the cross validation is made with all the points in the grid, while in the original CoMFA paper was using fewer variables. As you can see here, was shown an alert that the model was finished. Then if you refresh the page, you have the first line that is completed, and then you have the models. Okay, that is awful, of course, because we don't have we just have static model, quite good electrostatic, but the both model is not very good. We can go to the results and to look the results, static models, and we can show all of them. Okay, what we can do here? We can go back and make the model optimized with the random VPO, variable predictive optimization, without redoing any alignment. Clicking here, you have the choice to change the probe chosen between a set of your own. I suggest if you want to do a carbon as a methyl group, a polar hydrogens, an amidic nitrogens, and a carbonyl oxygen, and then to give the side the opportunity to change between 1 and 81 as the epsilon, the electric constants, then from 1 to 3.5, actually this is Python, sorry for this, step 0.1, and then we can change this by 1. These are settings, and with these settings, clicking on submit, you are going to make 10 random models. Okay, if I click here, in about 50 seconds I will have 10 models done, but I can go here and I have the model already done. I did this.
Zoom in a little bit.
I have to zoom. Okay. In this site, they advised me that you were not able to read. In this site, I'm looking at the site, at the original site, QSAR.com, where I have already done all the calculations. And as you can see here, I have improved the model a lot. And if I click here, the Q-square, the maximum Q-square, is jumped up to 0.67 after a lot of them. After what? I will show you. Okay. You see, these are all the settings, all the data sets we are using. So the 80, the angiotensin 2 converting angiotensin 2 enzymes with test set or without test set, 28 molecules. I ran 201 models, one basic one and 200 randoms, and I ended up with a very high good Q-square, even higher than that than one was published in the latest papers. And then I did all the combinations. Then what I did also, I should also almost finished the others. Then I did also test the same calculation, realigning the molecules. That is not part now of it, but I did something like almost 500 models, and with 32 by 192 by 3 conformation analysis alignments, and ended up with a very good models, even better. Let's see. The other should be done here. It's not here. Where is it? I got lost. Here. So the models have been finished. The first one is the best one you see is 0.2 with just 10 alignments. We got from negative Q-square from positive. If I run again, I can run again the same settings. Imagine we have billions of combinations here, and we have just chosen randomly 10, as you can do this. But there are some users can have more combinations, as I can do, and I can run 100, and then I can submit 100 models, and then we can switch while the server is making the calculation. As you can see, is updating editing now. I did 200 of them. If I go here to see the models with the realigned molecules, here I can compare all of them. Where are they? Okay, I don't have here my CoMFA, my dataset, my running jobs. No, it's not here. Molecules. I have two molecules. So here, CoMFA, and then compare models. Compare models allow you to compare models differently aligned. Okay, and then if I go here, I end up with the best model, that is 0.67, and then I can go here. Where is it? I can close it. Too many of them, I know. And then I can go here without test set. That is actually the same they did in the latest paper. If I go here and then I select the molecule, the CoMFA model here, and then I compare them with 28 molecules as training set, I can have a Q-square of maximum of 0.6. So actually, if you go back to the models they have published, I remember here, that is the paper from an Italian group. They made the original alignments. These are the molecules, and they got, so these are the Q-square. They used the goal and grid, and these are the models. You see, actually they got 0.48, 0.46, and 0.52 maximum. So this they did, although they were scaling and making some selection of variables to improve the model. In our, no selection was done. So this has shown you how to make a model using an already aligned molecules training set. So let's close this window. Okay, just to remind you, you can place questions on. Come on, this was cancelled. Okay. Okay, you can place questions written on the YouTube site, and then at the end of the seminar, we will try to answer to selected of them. Then I showed you that we are going to set also models on or structure-based aligned molecules that are actually from here. Okay. Okay, these molecules were taken from a paper from 2018 from Manuela Sabatino study in my lab, and these molecules were taken from 25, actually, if I remember, maybe more. It doesn't. Okay. That they were taken from. Okay. I don't know. The web is stuck somehow. So the molecules were taken and aligned by structure based, and we made 3D QSAR and combined models. We are not going to see the combined models, but we are going to see the models by 3D QSAR. And as you can see here, I'll show you the original numbers using the autogrid force field, and we ended up with a Q-square, very good Q-square, 0.8. With either leave one out or leave some out or leave half out, very good indeed yet, or also. And let's see how CoMFA performs with the same data set taken from this one that I cannot share right now, but I will share in the near future this data set with you. So let's see, I have the data set already done.
Only this is because
Okay. I don't know why it's not working. Come va sta tabella all'altra?
alt
Okay. Here I have the model already done, but I will show you the model from scratch. Okay. I go to the site on my PC. I go here in application. Again, Pymol edit. I make a new data set. You see here, I will show you later that the 100 molecules that were running in a few minutes they will be done. So I call this dot 1L. Okay. Then I know there were pKi on enzymatics, and then this was an enzyme, and the molecules were already pair aligned. I make the data set again, and I load the molecules. Then I go to choose the files, and then I know the molecules are somewhere here. So there were 15 files, 15 molecules for us training set. And while we were developing the models, the paper we were writing there, other 10 complexes were released, and there we used that test set. Then choose the activities. And here are the molecules already loaded, preloaded actually, and then I load. I'm sorry, I know that I have a big screen and maybe you don't see very well, but you know, I need you to give you the idea how to work with this site. Once the molecule has been loaded, I can load also the test set, choose the files, open the activities. What in the activity files? I will show you how the activity file is made of. Load molecules. Now I have 25 molecules loaded, and then I can run the models here. I go to Pymol edit. I did an error. I selected all of them as a test set, train set. No, okay. I thought I was wrong. Okay, I can go to CoMFA. And then I will make the full model with the full settings. And in a few seconds, the model will be done. Here we have bigger molecules, but you see, just click here, you have the molecules. Here is a quite good models. Not as good as the one was published with this probe, but I can make a random VPO here again with the same probes. I like those. I choose this because are the most similar to the most frequent atoms in a protein. So the 4 atoms. Then I go to choose this 81. So this is because we don't know the dielectric constant inside the protein. Somehow in some protein, deep inside the protein, the dielectric constant is around 6, 8, but in open part of the proteins it's 81 as in water. So it could be also a mixture of that. 3, 6. This is the grid spacing. Then I leave this, is okay. Then the cutoff value, how much energy we want to consider, and then how to prune the data. We don't know the molecules to be investigated inside the molecule, so this is going to cut some information also. And then we're going to make 10 of them. Submit. Okay. You see, here is telling many models already done. If I update, I have all of them already done. And if I go here, already I have from the C.3, I have a Q-square augmented, increased of 10% almost. More than 10%, 15% more or less here. And if I run 100, I will end up with 0.8 as I was. I got here 0.9. For this data set, I got a Q-square of 0.905, running 200 BPO combination. So from billions of combinations, I could be very happy with this. I don't want better than this. So this is the best one. And then you can also run the models for predictions. Right now we can go to see the results. We can have the plot, the names of the molecules, the experimental activity, the fitted or predicted, and the error, the cross-validated data, the error in cross-validation, and the molecular training set. But we don't have any point that is telling you there is any test set, because we didn't tell the model to make any predictions. We can go back, make the same model once we select it. So we are going to select the best one. Imagine this would be the best one. We can replicate it, and taking everything as the same, we can change here, apply model to test set molecules. 2, and submit. And in a few seconds, I will have a model with a test set predicted. Here is showing here. I'm going to follow this. I have here now true as the prediction. I go to the results, and I go to the experimentally calculated prediction. And now if I show all, I go down, I have here the molecules that have been predicted, the test set. And here you have the test set shown. If I deselect everything, I have the low active molecules badly predicted, as it is normally in any QSAR. In any QSAR you have always a J-shaped fitting procedure, because you are going to give the low active molecule the same probability to binds. That is not actually. But the model is able to recognize the most active as the most active, the second most active as the second most active, and in a case of a virtual screening, I would have filtered to these two, and I would taken 4WVL and 4ER3 as the molecules that has to be selected for synthesis. Of course, they have been already synthesized and complexed. What we can do here also, we can go back. We don't have the possibility to study more the data set here, because we don't have the map. You see, the maps are missing. As I showed you, the most interesting features of any 3D QSAR is to analyze how to modify the molecules. Then we can go back here to the best one, this is the best one, and then we can highlight the best one that with the true prediction, and then generate maps. And the maps are going to be calculated. In a few seconds they will be ready, hopefully. These are thousands and thousands of points around the molecules. Okay.
Rispondi a qualche domanda.
There are some questions, I know. Where are they? Here. Oh. For instance, one by chance. How do we decide the grid spacing? You don't decide, you explore the grid spacing. Because you don't know a priori what is the best grid spacing to have the best models. So what I can suggest is to start with 2.0 because it is faster, and then to investigate between 1 and 3.5. Yes, this will be recorded. This session will be recorded. It is possible to align molecules by ourselves also in the website. Yes, you can do that. Of course you can do that. The site was born just to do that initially. Questo.
Sì.
Mustafa is asking how we must choose the best model based on the highest Q-square value or PC number. Okay, I will give you an example here. Imagine we have these models. Okay, the maps are ready. Imagine we have these models, and then we have Q-square with the static electrostatic. We have three models actually. One considering just the static field, one considering just the electrostatic field, and one considering both of them. I suggest you to use this, but in some cases you don't have a very good model using both of them. Then you have to stick in one of these two. Okay, with the static and the electrostatic fields together, we have the highest Q-square at 6 principal components. But if you go back, we have models very close in Q-square values. What you have to do is to calculate the increment of Q-square or the decrement of the step starting from the first one. So if from first principal components to 2 principal components you have an increment of more than 5%, then you have to consider the second component. If you have an increment in the third, then you have more than 5%, you have to consider the third principal components. Very likely the best one is a 2 principal components here. And also if you consider the step decrement, if you have a decrement lower than 5%, the further principal components has not to be considered. So when to use Q-square decrement and step decrement? If you have very good models, the decrement in step is always tiny. So better to go with Q-square. Okay, it depends. The best way is to use that step, but sometimes the step is always lower than 5% decrement. So now we know the best model is a 2 principal components. For these 10 models we have done, we have a Q-square of 0.656 and then an R-square of 0.9 almost. Can we read this? Yes, now we can read. We can go to view dataset contour maps, or even we can go deeper. I'm not going to explain this in details because it will take too much, but we can have a look at the maps. So here, clicking here, we can have already all sets with the classical CoMFA 90% contribution for positive steric increment or negative steric decrement of activity associated. So what I can suggest, you have a bunch of things to see here. This is just for steric fields. You can watch at both model. Normally in the original CoMFA, steric plus electrostatic contours was called both. So that's why I use both. And here it is called both. Here you can have all of them, and actually when you click here you can form maps. That is quite difficult to read. But here you have the maps. You can switch it on and switch it off. You have a bunch of them. You can just have a look at the steric coefficients. So the coefficient of the QSAR equation that are going to weight each point of the grid. So you can have steric coefficients positive, negative. You can have steric coefficient multiplied the standard deviations of the points, or you can have steric coefficient multiplied by the mean. My personal opinion is to focus on the steric coefficient multiplied by mean of each point in each grid point of the grid. So 90% is the 90% of contribution to the activity. So we are going to see now what are the points that are most important for the activities. I can switch it off this, put in 0, and put in 0, and just focus on the positive steric maps. And also I can also focus on the most important maps. For instance, putting this on 50%. Okay, what are the best point, the most important point for these models? The most important point are this, and this. And the model is telling us that we should first increase sterical hindrance here, here, here. Okay, and if we are going to increase, we can have some other info for the positive steric hindrance. This means that if we are going to modify one of these molecules to increase the occupancy of each polyhedron here around the molecules, likely we could end with a higher active molecules. Then if we switch off this and we switch on this, the negative one, the model is saying better to cut out here something of steric. And actually, as this molecule are derivative of the S-adenosyl methionine, the cofactor of the enzyme, this is the methyl of the methionine. Very likely is detriment of the activity if you are going to increase the steric hindrance here, of course, because this is the methylating agent. Then we can focus also on the electrostatic mean positive, 50%. And then it is going to tell us which part of the molecule we have to increase the ability to donate hydrogen bonds. As you see, the model is correctly organized here. These oxygen are going to give to accept hydrogen bond, hydrogen bond acceptor, sorry. And maybe we should insert here something, because somehow some other molecules, the most active, for instance, has not substituted here that are suggesting to make hydrogen bonds. So maybe to insert here in the most active compound some different group here, we could even increase the activity. Although this most active compound, as you can see here, is picomolar. So we can have even higher active compounds, just likely modifying here. Or we can increase the ability to donate hydrogen bonding here. And then we could put here an oxidryl here, an alcohol, to have a donating hydrogen bond, or an amino group, or an SH, for instance. And then what we can do, just draw the molecule in PyMol edit, insert the molecules, align with the same method, and then in this case we have to do some molecular dockings because these molecules are inside the receptor, and to see if the docking is able to put the molecule in the correct way, the molecule has been predicted more active. So these were the two sets. Where is the data one? Okay, I can go to data sets just to show you the molecules have been, the compounds on 82 as finished. We can have at 100 models done, sorting them, and then we have increased from negative to 3.36. We can even increase more this. Okay? So this is the way to interact with the server. Make a model and to increase the model without selection of any feature, using all of them, optimizing the alignment or the pretreatment. Okay, let's jump to make some model from scratch. As you can see here, okay, I close some windows because it's too crowded. Okay, I go here and I select this, open on here. Okay, as I told you, I have selected two papers from Journal of Medicinal Chemistry ASAP articles. That is loading from GMedChem here now. Somehow it's low. Okay, this was one of the two articles I selected. Here we have more than 50 molecules available. If you go here in support informations, you can have the CSV files. That is actually the one I'm going to show you. The QSAR. Okay, and here the files, and the files should be this one. Okay, this is the file that is available from Journal of Medicinal Chemistry. Actually, these are 30 molecules. I was wrong. Okay, here we have the SMILES. I hope any of you is familiar with SMILES structures. Actually, these are zero-dimension molecules. SMILES is a very fast way to draw molecules, and it is the universal accepted format for almost all software and molecular modeling. So we have a columns with molecular weight and a column with the activity. What we can do, taking each molecules and separe all of them in different files, as it is shown here. I have already divided them, so I have each of them divided, and I have just the SMILES structure. Inside SMILES called compound 10A. That is the name 10A was given in the papers. And then I have the activity files. That is IC50. I don't know if you can read, but I can read for you here. And that is a list of name of the file without extensions, and the activity expressed as in molar, I think, if I will remember. No, it's in micromolar from the paper. Okay, let's see. These are the experimentals. Nanomolar. As you can see here, the activity were expressed as nanomolar. We need to take this information. So once we have this list compiled and the different molecules divided for each of the molecules, we can go on the site again. We can open quantity. Okay, then I go to my molecule, my sites. Okay, I go to application again, PyMol edit, and I can add a further data set. Then I call JMedChem1. Okay, I have IC50, enzyme, IC50. These are generic enzymes. These are not aligned, these molecules. Okay, submit. I create an empty data set, and then I load molecules. I'm going to load the files again here from scratch. JMedChem. I take all the smiles molecules, 35 of them. Then I choose the files containing the activities. The IC50 I have prepared. Telling this is nanomolar, and just in case you don't have an activity, this number means that it's giving to a molecule that is not going to pair the activity 6 nanomolar. I would say 1 nanomolar, but it's not going to happen, this one. Submit. This is going to read 35 molecules. This is going to associate correctly the numbers. Okay, the activity was given in nanomolar. The compounds, the names was recognized. Okay, load the molecules. These are from smiles. Meanwhile, the server have been converted into 3D. The hydrogens are there, believe me. So we can go back, and right now, if I go here and to try to make a CoMFA, I cannot do a model. Submit. You see, if I submit a model on this molecule, the server is warning me this molecule has not been aligned yet. So this is important. What we can do now, we go back and we need to make an alignment rule. And then we are going to select PyConfSearch, make ConfSearch. There is no conformational search yet. And then we can make ConfSearch. The fastest one is RDKit. Leave this as it is to make it as faster as possible. And running. Now the server is making conformational search for each of the 35 molecules, giving output as maximum 50 conformational for each molecule, using 50 iteration in the minimization, and using the universal force field for the minimization. This could be, I have already the model done, of course. These were the model, 35 molecules. I have done here conformational analysis, my ConfSearch, okay. Where is it? Web. Where is it? This one. Okay, I've done RDKit, 50 conformation, 50 max iteration. Okay, as I just shown you. Here should be finished. Yeah. know if already finished the conformation analysis. It's not, it takes some minutes, but we can go to see that we can have, so the formation, once you have run the conformation, you can have a look at them, results. These are the conformations for one molecule, this one, compound 10A. If we click on 10A GM, we just have the global minima of this compound. On the right, you have a table telling you for each molecules, for each conformation analysis, what is the least active, the most active, the heaviest, the longest. 16 combinations by 2, because for each conformation analysis we have also the longest conformation inside the conformation analysis. This is because while testing the method, we realized that sometimes the alignment on the longest conformation gave very good results. So we have 32 combinations. Okay, once you have the conformation analysis, you go back to conformation analysis. You can download everything, and then we can just highlight this and to make alignment. Click here on the align and to open a new Windows and to align all the conformation analysis using two methods, RDKit or Shape. Shape by Mikko Vainio. There is a free software for Mac OS, Windows or Linux. And then we can select the scores. We can have up to 4 of them, and also the template, 16 different templates, and we can check to use the longest or not, or the global minima for each conformation analysis. Moreover, we can also select an uploaded conformation, for instance conformation extracted from a crystal structure, or a molecule among the train set that is not among the 16s that have been selected. So actually, if you have 35 molecules, you can have 35 templates, 36 actually, with the upload conformation. But if you select one molecule, you don't have any rationale. If you select one of these, you have a rationale to say, I have chosen the most active, the one that has the lowest number of hydrogen bond donate or accept or whatever. So this is a rationale to make the alignment rules. So if, for instance, we are going to take the most active using the longest conformation, submit, and then the conformation is going to be aligned. Okay, but it is still running. This is finished. We have the conformation done that we have just sent. These are the conformation for the compound 10A. Okay, we can also have the conformation of compound 11B, that is the most active. It is not working. Okay, we can select the global minima of the molecule and also all the conformations. What information is giving you to click here? This molecule have been automatically aligned on the most stable conformation, and these are giving you how much a molecule is flexible. You see, this molecule is very flexible. So once we have the conformations, we can run the alignments. For professional user or collaborators, the multi-align can be used. That is going to make a combinatorial use of the alignments running up to 192 combinations. That is going to take almost 1 hour to make 192 models for me, because I can use up to 10 or even more cores to make the calculations. any plain user has one core available. Okay, but it is quite enough. My students are able to make for their exams up to thousands of models easily in a week. Okay, let's go to make the models. Make a line also here, just to take the best score, the least active, most active. Also here, the longest, submit. Could be very fast if I will remember. And also, we have also the results here for the models. Here. From scratch, I ended up with models up to 0.59 of Q square. That is not bad for 1 day work, I would say. Let's see if the alignment is done. Questo coso mi dà fastidio. Okay, let's see if finished. The alignment is not finished yet. Okay, so we could end up with a very good model here, but these were obtained with this type of a calculation. I will show you well. So this was the train set, the 35 molecule. I made 194 alignments. They ended up in 122 childs because some templates were the same, so they were doubled. So from 194 combinations, just 122 unique models were obtained. Then if I click here and I go to
CoMFA.
yes, I know. Web. CoMFA, and then I have compare models, and I have the best models here. Okay, this was obtained using the most rigid compound with the RD kit alignment. But if you want to go to the molecular alignment rules, you have to go back to the alignments you have done. So you have the rules to apply it for the alignment of new molecules. That's good. It's still running. That's strange. 35 molecules should have finished. Okay, let's see if there are some questions. What are you, Latif? I don't know how to say what is the surname of the last name. Can I have the file? Which file? Okay, how do we choose the best alignment of a dataset? You choose the best alignment on the Q square value. Molecules that act as dual or multi-enzyme inhibitors. Actually, it could be feasible, but it's not yet implemented. With PLS, you could give 2 activities and to have the best for both activities. So with PLS, you can give more than 1 activities, and to be, but it is very rare to have that. I suggest you to develop 2 models for each of the activities. It is very unlikely that one alignment could be useful for 2 targets. So another questions, quick learn, how many minimum data set required to generate 3D models? Oh, okay. The minimum data set, I suggest you to have at least 15-20 molecules. So if you have 30 molecules, I suggest you to divide into 66% into training set and 33% into test set. So Kaushik is asking a paper on which CoMFA analysis has done. If you look paper from me, there are a couple of them that I have done using grid combined with GOLPE on reverse transcriptase inhibitors, where I gave a very deep explanation on how to read 3D QSAR models. So other questions? I don't know if I are finished here. Yes, so the alignment is finished. So if I click here, I go to read the alignments, view molecules, and these are the molecules aligned. Not bad by eyes, okay? Not bad indeed. So these are 35 molecules already aligned. If you click here on PyAlign and we select PyConfa, and then we make a model on this, hopefully we could have a model that could be named like model, with model. Submit the full one, and this is not going to take a lot, 35 molecules, maybe a minute. So this is now making calculation on GPU, and this PC has a 2007 NVIDIA card. Okay, this is done, and you see we ended up with a positive Q-square with just one alignment. We can run VPO on this, for instance, okay, with the default settings, 10 models. You see they are running 10 of them. And then in a few seconds the other should appear here, the results. Okay, other question to be answered? Okay. Okay. Let's see. Yes, the webinar is being registered. Okay. Slightly better, just a little. Okay, just to back on the questions from Sebastian, he asked, how do we choose the best alignment of a dataset? The best alignment is the one that fit better with the structural activity relationship also. So if you have two alignments that are giving you the same or very similar Q-square values, first, you select the one that has the fewest number of principal components. Second, you set even number of the same number of principal component and Q-square. You take the one that the highest value of Q-square on the static model, and then at the end you select the one that has a good fitting with the structural activity relationship given from the original authors in the paper. So you see, we ended up with new models up to 0.334 Q-square. According to what Kramer published, this would lead to any not to a model without any chance correlation, because he wrote that a CoMFA model with a Q-square of 0.25 is not going to suffer of chance correlation. So actually this could be good, but the R square is too low from my point of view. The R square should be at least 0.7. But if you focus on the model just obtained with the steric field, we have very good Q square 0.5 and very good R square at the maximum value. If you go to see the results, so we have actually, yes, the best one is 5 principal components. As a rule of thumb, the number of principal components should be 1/5, or at least at maximum 1/5 of the number of the molecules in the training set. This is the best ratio. So, as you seen, we have developed a very fast model on a fresh released molecule from Journal of Medicinal Chemistry. These are not yet published, these results, of course. So let's see to have a look to the last data set. Okay, just close some window. Again, the last data set was for another paper from Journal of Medicinal Chemistry. Okay, the paper was this one. So actually these are epigenetic inhibitors. These are going to interact with a protein that is going to be a reader in the epigenetics. Okay, and bromodomain are going to read molecules that are proteins that have been modified from other enzymes, post-traductional modification. Okay, and here again, in Journal of Medicinal Chemistry since 3 or 4 years, maybe more. Come on. There are supporting informations you can download. Here we have also the molecule co-crystallized with the bromodomain, and then you can hear the molecules as smiles again. Then I took this and I made the models, and these are the models. After align them, optimize them with variable predictor optimization, I ended up with Q square of maximum. Oops, these are not Q square. Okay, the maximum Q square is 0.74, 52 molecules. This is a very good model. These are the results. The procedure is always the same. You take the comma separated variable files, you make the different SMILES files, you make a list of the activities, you import all the molecules, you run the molecule, the models, the alignments, the conformation analysis, and you make a bunch of models and you select the best one. The best one for what I did actually three days ago, because these papers was released the 21st of March. And then was the best one. Actually, I maybe could select this one. I have to calculate if 32 is higher or lower than the 5%. Okay, maybe it's not. Okay, how can I do? Here. Okay, can. Okay. The 0.7. Oops. Yes. Minus. No, is divided. Sorry. 0.32, that is the difference between these two, divided 0.7 point
Exactly.
32 divided 0.713 by 100. 4.4%. So actually it's lower than 5%. So the best model is a 4 principal components, 5 principal components. Cool. So this is the best one. And actually you can see here the trend of the Q square and R square with a higher number of principal components. And as you can see, this is the 5, 6th, 7th, okay? And this is the trend of the standard deviation error of calculation and standard deviation error of prediction. This is in fitting, this is in cross validation. And we can go also to see the experimental predicted activity, and we have a very nice plot at 5 principal components. And down we have the fitted or predicted activity, predicted in the case of test set. Here we have the fitted in the training set and the cross validated. That is not bad indeed. Okay. Let's see what I did, just to show you. I am almost finished for today. I did also the docking on this data set to show that in a day I did also some dockings, okay, and combined models. And I ended up with 0.5 almost model of combined. It is very rare to have a very good model. For .1L we had a very good model, but if I go here to the results, we can have the best model at maybe, yes, at 4 principal components, and then we can have also a very nice plot here telling you what are the most important residues interacting for the best model using steric, hydrophobic and hydrogen bond interaction. And here we have the view of the ligand with the 4 most important residues around the molecule. You can download this and to have the possibility to read this in Chimera. So this is the last for today. I have given you a lot of data, a lot of points to start with, and I want to thank all of you. I go back here. And I want to thank Alessio and Dylan, and I want them to come behind me. And what I can say, happy 3dqsar.com for all of you.
Hello, Ron. Hey. Are there any more questions?
There are many questions. I will try to answer, but I would be grateful to you if you could place the question on Pi forum, so that the question will be for anyone looking at the answers.
Could you show where it is?
Yes, I will show you the Pi forum. If you go here, Pi forum, and then if you go here, once you have enrolled the site, you can place questions here. There are a few of them already answered, and happy 3D QSAR again. Bye.
Bye.